Right, so on to second order homogeneous linear differential equations now. Okay, so a bit of a mouthful there. But yeah, that's what we have to deal with in advanced science. So differential equations of the form A times by d squared y by dx squared plus b times by dy by dx plus c times by y equal to some function in terms of x, where a, b, and c are constants, are fairly common in most branches of applied maths and are what we call second order linear differential equations. Okay, we have the two different types. We have homogeneous and we have non-homogeneous. So when the right-hand side is just equal to 0, in other words, there isn't a function, then the equations are referred to as homogeneous. And when it doesn't equal 0, and there's lots of different types of this, so look forward to that, then the equations are referred to as non-homogeneous. So we're going to start with the homogeneous ones. Okay, so they're going to look something like this. Okay, so the general solution to such an equation must include two arbitrary constants, in other words, two different constants, to be completely general. Okay, this is important later on when the roots are real and equal. Okay, so just bear that in mind because we're going to have different types of these. Okay, so next up is a proof of sorts. Okay, this is quite complicated to follow, so do your best. But the bottom line is the actual solution to this is relatively straightforward. So the proof isn't so important. Okay, but the idea is because of these two arbitrary constants. Okay, if y equals a function in terms of x and there's y equal to another function in terms of x, a different function in terms of x, and if they're both solutions to the equation, then so is y equal to f of x plus g of x, and this is the proof of that. Okay, so in terms of that second order homogeneous differential equation that we just looked at, equal to 0, so basically replacing the y's with f and g. Okay, we'd have a times by d squared f by dx squared plus b times by df by dx plus cf equal to 0, and vice versa with the g. Okay, if we were to add these together, we would get something along the lines of this, and we rearrange it to make life slightly simpler. Okay, and then we could take a out as a common factor, b out as a common factor, and c out as a common factor of those different sections. Okay, and by the additive law of differentiation, okay, in other words, when we add two derivatives together, okay, we can just say it's the derivative of those two things individually. Okay, so the second derivative times by a of f and g, and then likewise with b, and the first derivative of f plus g and c and f plus g at the end there. This tells us, this is the proof that f of x plus g of x is a solution to the differential equation. Okay. That being said, because y equals ae to the mx, for some a and m is a solution to the first order linear differential equation, b dy by dx plus dy equal to 0, it is reasonable, okay, it is reasonable, I'm telling you, to consider it as a possible solution for the second order homogeneous differential equation. Okay. That being said, okay, we're going to try and prove it nonetheless. Okay, so if y equals ae to the mx, and dy by dx will equal am e to the mx, and d squared y by dx squared will equal am squared e to the mx. Okay, we differentiate that with times by another m, so we get am squared e to the mx. Okay, so if a equal ae mx is a solution, it will satisfy the original equation. So substituting in the original equation gives. So the original equation was a times by the d squared y by dx squared plus b dy by dx plus c y. So we're just taking these three values here in terms of what we've got for y, dy by dx, and d squared y. We're substituting into that original. So it's a bracket am squared e mx plus b a m e to mx plus c a e mx equals 0. Okay, right. If we're assuming that ae to the mx does not equal 0, okay, which we have to assume to be able to divide, we would get a common factor out as ae to the mx, and it would leave am squared plus bm plus c equal to 0. Okay, and obviously if we divide by that ae to the mx, okay, then we'd be left with am squared plus bm plus c equal to 0. Okay. That therefore means that the solutions to this quadratic will provide two values of m, which will make y equal to ae to the mx a solution. Okay, complicated? I told you. So if we call these two values m1 and m2, okay, so they're different values of m, so we're just going to call one of them m1 and one of them m2, obviously. Then we have the two arbitrary solutions. Y equals ae to the m1x and y equal to the be to the m2x. So we've got two different labels there, a and b. Are going to distinguish the two arbitrary constants as well. Okay, So by the first theorem, the first proof that I tried to give, this gives the solution of those two solutions added together. Y would equal ae to the m1x plus be to the m2x. Okay, so note the two arbitrary constants needed for a second order linear differential equation. This ensures that all solutions are covered. So the equation am squared plus bm plus c equals 0 is called the auxiliary equation. This is mainly what you're going to be using with all of that proof, all of that information that you don't really need. That's just showing where this comes from. But this is going to be your life throughout second order homogeneous linear differential equations. This is all you really need to know, and that and factorizing. Okay. But the point is, when we factorize, obviously we get different types of roots. So the nature of the roots can be very different. Okay. So I'm going to go through the three different possibilities with you now. So the first one, the obvious one, when the roots are real and distinct, this is the one which we most commonly have. Okay, so we start with our different second order homogeneous linear differential equation, and it would look something like this. Right, all we actually need from this, okay, is the coefficients of each part. Okay, and we can take them out and create our auxiliary equation and get m squared, because there's a 1 here, so it's m squared, 1m squared minus 5m plus 6m equal to 0. We factorize this, and the point is we get two distinct solutions. Okay, and then our general solution is just y equals ae to the 2x plus be to the 3x. Okay, we're not finding a particular solution for this particular question. Okay, but if we did, then that would give us a value for a and b. And what would happen is we'd be told in the question in the same way, there'd just be a second part to it, and it would say x when x equals something, y equals something. And it would probably also say when dy by dx equals something, x equals something. Okay. In which case you'd substitute them in and you'd get some kind of simultaneous equation, like this one. Okay, so we're going to find a particular solution of this second order homogeneous linear differential equation. Start with the auxiliary equation, which is 2m squared plus 7m minus 4. Factorize that, so you're going to have to be clued up with your factorizing, but it's 2m minus 1, m plus 4 equals 0, in which case m equals half, or minus 4. Okay, so this gives us a general solution of y equals ae to the half x plus be to the minus 4x. But we want a particular solution, so we're going to use all of these values. So y is 1, dy by dx equals 2, and x equals 0. So here, obviously, if we're going to be left with an a and a b, okay, we need to get rid of the x and the y. We've got four variables here, okay? We can get rid of two of them from this question. Dy by dx is going to come in a second. But the problem is, if we substitute an x and a y, we're going to be left with an a and a b, okay? There's nothing wrong with that, okay? 1 equals a plus b, but hopefully by now you should recognize what's probably going to happen next. If we've got this kind of equation, we're going to need a second similar equation, and we're going to have to solve by simultaneous equations. Right. On that note, there's three different ways to solve simultaneous equations. Everyone always just tries to go for the elimination method. That's fine. There's nothing wrong with doing that. But more often than not, the actual substitution method, in other words, if we rearrange this to give us a or b equal to something, we can substitute in and find it a lot easier that way. Okay. But in this case, the point is we need to use this dy by dx. If we're going to use the dy by dx, given this is our equation, we need to actually differentiate this. Okay, so we're using the x equal to 0 and the dy by dx equal to 2. We're going to differentiate this, and just remember the chain rule when you do that, and then substitute in those values to give us 2 equals a half a to the minus 4b. Right, if you use simultaneous equations, and don't worry that I've done this in one stage, you can do it in however many stages it needs to get you your a and your b, but the point is you get those two answers. Right, that's not your answer. Your answer is those substituted in, okay, which gives us something like that. Right, when the roots are real and equal, though, it becomes slightly more complicated, because the problem basically is that when we go into the particular solution, or sorry, the general solution, we'd have the same m values and nothing to distinguish them. Okay, in which case we'd have something like that. So a plus b is equivalent to a single constant, and as I said earlier, we need two arbitrary constants. So there's another proof for this. I've not done it in here, but the point is it's very similar to kind of what we did in partial fractions. We're going to shove an x in the second part, and that should distinguish between the two different parts to this for when the roots are real and equal. So you can only use this when the roots are real and equal. So again, you're going to have to memorize these different forms. Okay. Right, so example here, it's just a different way of showing it. Y double dash and y dash just basically means d squared y by dx, and dy by dx, it's just y differentiated. So you'd get your auxiliary equation, m squared minus 6m plus 9, you'd factorize it, and then you'd discover that m equals 3 and 3 only, okay? In which case there's the repeated roots, in which case our general solution has to contain the x. So a e to the 3x plus b e to the 3x wouldn't work, because then we could have basically a plus b as a common as a factor, which would just equate to one constant. We need to be able to distinguish between them. They need to be arbitrary, in which case we have to have that x in the second part. Okay. Right. So using this method with a particular solution, you'd end up with something like this. Okay. It's the same idea. You get your auxiliary equation 9m squared minus 6m plus 1. You factorize it, and then you'd get equal roots, m equal to a third. So for your general solution, it's a e to the third x plus b x e to the third x. And then you want to find your particular solution using the given given values we're looking for from the question. So y is 1 when x is 0, and y equals 4e when x equals 3. So we don't actually have to differentiate this one, but we're still going to use simultaneous equations when we substitute them in, and we get something like this. Okay. And when we solve it simultaneously, we get a equal to 1 and b equals 1. Okay. So because of this form here, okay, we can basically, all that we're doing is just dividing through by e. So 4 equals a plus 3b, and using the value that we've got from the first part, a equal to 1, we can substitute in basically 3b equals 3, in which case b equals 1, and then we get our particular solution. Okay. Right, the third and final part is basically going to involve when we can't find the roots. If we can't find the roots, we can't get an answer. But in terms of not finding the roots, what it basically means is we can't square root b squared minus 4ac. You know that from National 5. But often in maths, we want to be able to kind of go on a little bit further, and we want to deal with the square root of a negative number. Okay, so this is where I comes in. You'll have seen this a lot from around maths. Hopefully, if you haven't, don't worry. But basically, from now on, if you have the square root of a negative number, you can introduce this term I, which is an imaginary number. Okay, so I squared equals minus 1. In other words, I equals the square root of minus 1. Okay, so in this instance, we want to kind of go one step further. So we want to actually use a value, even though we can't find a value, okay, because we're going to find the square root of a negative. Okay, we can't necessarily do that without imaginary numbers. So we're introducing these imaginary numbers to help us get to the next stage that we need to. So these complex conjugates is what we're going to use, or the form m equals p plus or minus qi. Okay, Mr. Shepherd's going to go through some imaginary numbers with you, so this will make more sense, but I just need to touch on this just now. Okay, so just bear with me a second. I'll give you some more definition on this in a second. But the general solution of these types is of the form y equals e to the px times by a sine qx plus b cos qx. A and b are still constants, but we're obviously going to find a value for p and q. Okay, they come from our imaginary number. So if I go through this example with you, you've got d squared y by dx squared plus 4 dy by dx plus 13y equal to 0. Okay, so do the same thing. Get your auxiliary equation, m squared plus 4m, that should be plus 13 equals 0. Point is, you can't factorize that. If you factorize in the same way as me, you're looking for the factors of 13, add to give you 4. Okay, so there are none. So you know this isn't going to work, but you still put it into the quadratic formula anyway to get this value here. You can see this p plus or minus qi, that's going to come from this top row here, if we can simplify with a 2a. Okay, so I'm going to pop those values in. You've got your a, b, and your c are 1, 4, and 13. And when you put them into the equation, you get something like this. Minus 4 plus or minus the square root of minus 36 all over 2. Right, there's a couple of ways of doing this whole minus 36 square rooted business. Okay, you can take out minus 1 and replace it with I squared. So as I said, I squared equals minus 1. Or you can just do it in terms of surds. Okay, you can think of this as the square root of minus 1 times by the square root of 36. Either way, it simplifies down to 6i. Okay, so minus 4 plus or minus 6i over 2. Right, we want it more in that form, so we want to deal with a p and a q individually, so we don't want this 2 on the bottom, but with this one we can divide by 2 nice and simply. Okay, so it's minus 2 plus or minus 3i. All we need from that is our p and our q values. So p is obviously going to equal minus 2, and q is obviously going to equal 3. Okay, and then we can just substitute these into our equation. So y equals e to the minus 2x bracket a sine 3x plus b cos 3x. Okay, yes, you do have to remember that form, but we're going to have some more practice on it with our non-homogeneous equations as well.